Hello there. In this lesson, we're going to learn about double displacement reactions that form precipitates. And so in the example here, you can see that this reaction has produced this yellow substance that's actually a solid that will eventually sink down to the bottom and form a little powdery layer at the bottom of the beaker there. And so that's a reaction that makes a solid from two aqueous solutions, and so that solid would be called a precipitate. So precipitates, as you can see, are the solids that form from reactions where you start off with aqueous substances and you end up with solids. So those are the precipitates, the new solids that form. So if a substance can dissolve in your solvent, that is termed soluble. Now the solvent that we're going to use throughout this course is just going to be water. We're not going to use any other solvents. And then if it won't dissolve, then that's going to be termed insoluble. And it's those insoluble compounds, if they form from a reaction, that make the precipitate. So insoluble precipitate. The reason why some solutes are more soluble than others in water has to do with the attractive forces between the particles in there. So water, if you recall, has an oxygen and it's got the two hydrogens, right? And oxygen is more attracted to the shared electrons than the hydrogens are. And so the oxygen side gets this partial negative charge and the hydrogen side gets this partial positive charge. So it's a polar molecule, means it's got two poles, it's got a negative side and a positive side. And so it'll be attracted to the ions in an ionic compound. The question is, how strong is that attraction? So if the ions have a greater attraction for each other than they do for the water, that'll be insoluble, and that'll form your precipitate. If the ions are more attracted to the water than they are to each other, that'll be soluble, and it would just dissolve and you won't get a precipitate. So that attraction between those particles or for the water is what makes solubility happen. In order to determine whether a compound will be soluble or not, we're going to use solubility rules. Usually compounds sort of dissolve in sort of a scale, like some are only a little bit soluble and then some are really soluble. And even a soluble ion will have a limit. There'll be only so much that can dissolve. So these soluble rules are sort of a simplification to be able to determine sort of quickly which ones you would expect to precipitate right away and which ones can dissolve quite a bit. So the way that it works is it's organized by anion. You see that all the ions on the left here are all negatively charged, and it gives you the basic rule over here, right? And then on the other side we got the exceptions. So most things when they're bonded to, in fact all things when they're bonded to a nitrate or acetate, will be soluble, right? Because that is the rule. Most things, if you bond them with a halogen, will be soluble. But there are a few exceptions. So if you have silver here with chlorine, then that's going to be an exception to the rule, which would make it insoluble, right? Below we have the rule for insoluble ions, right? And so the rule here is that sulfides are usually insoluble, unless they're with one of these exceptions, like group 1 or 2. Carbonates are usually insoluble, unless they're with like group 1 or ammonia, and so forth, right? So it takes a little practice, but you'll get used to using this little chart or something similar in order to determine whether or not your compound is likely soluble or insoluble. Okay, so let's practice a bit together, see if we can determine whether these compounds will be soluble or not. We'll start with this silver sulfate. So sulfate first, there's sulfate. So the rule is it's soluble. Is silver an exception? Yes, it is. So that makes it insoluble. Then we got calcium chloride here. Chlorine is a halogen, usually soluble. Is calcium an exception? No, so soluble. Lead nitrate. Nitrate's also mostly soluble. In fact, all soluble, no exceptions. So that means this is soluble too. Carbonates. So next we're going down below here. So carbonates are usually insoluble. Potassium is group 1. So that means that this one will be soluble because it's an exception to the rule. Hydroxides. Hydroxides are usually insoluble down here. And iron is not in this list of exceptions, which means this is definitely insoluble. And magnesium phosphate is our last one. Phosphates are insoluble. Is magnesium an exception? No, it is not. So again, insoluble. All right, so once you can figure out whether it's soluble or not, then you can put the state on. All your insoluble compounds will be solids, and all the soluble ones, as long as there's some water around, they will be aqueous. So let's see if we can work this out here. So we got a sodium, and we've got nitrate from our double displacement, and then we'll put the silver with the chlorine. So silver with the chlorine. Now, if you remember or you look back at your previous notes, you'll see that nitrates are always soluble, doesn't matter what they're with. So that'd be AQ for that one. And chlorine, being a halogen, is usually soluble, but with silver it's an exception, which means it's insoluble, so this will have a solid state. Next one, all right, we have lithium, that's going to go with the bromine, and we'll have calcium with the carbonate. So the bromine there is usually soluble, and lithium is no exception, so again, aqueous for the first one. Carbonates are insoluble, calcium is no exception, so that's our insoluble one, so it gets the little S for solid. S for solid. Now, equations with soluble and insoluble compounds in them can be simplified if you know the nature of the ions that are present. So if we know which ones are soluble and which ones are insoluble, we can do a little trick to pull apart the ions that are in the solution and then minimize the amount of writing that we have to do in our final expression of the reaction. So the main thing to understand is that whenever an ionic compound is dissolved in water, the ions separate from each other. They're attracted to water, they're surrounded by water molecules, and they're not bonded to each other. So you can separate them into what's called a total ionic equation. So for the first one, we'd separate the sodium ions from the chlorine ions, and we could say that they're aqueous still, right? That's more true to what's actually happening. Same with the lead, 2 plus, AQ, and the nitrate, NO3 minus, AQ. And you can also include the quantities. There's 2 of those, and there's 2 of each of these, so 2 and 2 and 2. And then on the other side here, we have sodium, which is positive, and we have nitrate, which is negative, and we have the lead chloride, which is not dissolved in water, is a solid. So you can only do this for aqueous compounds. And we've got 2 of these and 2 of these. So that's called a total ionic equation. Basically, all you do is just take all the aqueous ones and separate them into ions. Once you have a total ionic equation, what you can do is recognize that there are ions in there that aren't doing anything. They're not changing from before or after the reaction. And if they didn't change into anything new, well, there's no sense in them being there. And you can simplify your reaction. So we call them spectators, just like we did in the last lesson. Spectators, the ions that didn't actually change before or after the reaction. So you can see that sodium here is aqueous and floating around all by itself. And on the other side, there's the same sodium floating around all by itself, not doing anything. And likewise with the nitrate, floating around all by itself, nitrate floating around all by itself. And so what we can do is we can eliminate the spectator ions, the ions that didn't change, didn't bond with anything. And what you're left with is called a net ionic equation. And so you're left with the 2 chlorines, the 1 lead, and they came together and made this new compound that's a solid because they're bonded. And that's the actual reaction that took place. So in order to do that, what we can do is just complete the reaction as normal, and then you can identify the spectator ions and remove them. So let's do a couple here together. We've got barium and phosphate, 4, 2, right? And if you look up that on your solubility table, you'll see that it's insoluble because phosphates are insoluble and barium's no exception. And then we'll look at, we got sodium and nitrate, and nitrates are always soluble, and so we can leave that one as aqueous. So you can write out the whole net ionic equation if you like. Write out the whole total ionic equation. You can write out barium and nitrate and sodium and phosphate, and then the arrow and the barium phosphate, you'll leave that all together because it's a solid. And then the sodium, again, is separate. And the nitrate is separate. What we haven't done here is balance anything. So if I balanced it, I would end up with, well, we're going to need 3 bariums and we're going to need 2 phosphates, which means we end up with 6 of these. So if you go through over here, we got 3 bariums and we've got 6 nitrates and we've got 6 sodiums and we got 2 phosphates, and that's fine. And then you end up with 6 of these on either side. And then you look for your spectator ions, the ones that didn't change. So you can see that nitrate and sodium over here are the same on both sides of the equation. And so you can get rid of those. And what you're left with is 3 bariums and 2 phosphates, making barium phosphate solid. Right? These are aqueous. Now, if you want to speed things up a little bit, you'll notice that the spectator ions are always the ions in the aqueous product. So for the second one, we'll do this a little quicker. We'll put together calcium and sulfate, and we'll put together potassium and hydroxide. So sulfates are usually soluble, but not with calcium, so this is your solid. And hydroxides are usually insoluble, but not with group 1, so it's aqueous. So we can balance it out. There we go. And so since our aqueous ions on the other side are the potassium and the hydroxide, we know that those are our spectators. So we can just sort of slash them right out of the equation right here, take away the potassium, take away the hydroxide, and then we could rewrite our net ionic equation with just what's left to make this reaction. So calcium 2 plus sulfate 2 minus makes calcium sulfate, like so. Okay, hope that helps. We'll talk to you soon.